Hi, I'm Gavin. This is just a little podcast of an explanation of this bundle of joy here, the development of a peripheral heart monitor. Just a bit of information on what it's about, what it does, and what needs to be done to it.
This is the BioHeat equation. This equation is essentially governing the entire project. What we're going to find is the Q double dash. We get the small h value from the heat flux sensor, and the delta T is the temperature recorded from the two RTD units that are on the device. Now that we know our h value from our heat flux sensor, it can be applied to this kind of equation here, so the Q double dash from the equation previous. Everything you see in blue is the heat transfer through the skin, everything you see in red is the heat exchange due to the blood perfusion. Now, if I'm going to be entirely honest, most of the things here are constants. The only thing that's really going to matter is the small delta T, which is the time in which the probe is held to the hand, which is going to be about 30 seconds. We kind of remain that as a constant, and the omega value. Omega is the blood perfusion. That's the thing you want. That's the thing we're trying to find. So everything can be rearranged to the TA minus the TV is the temperature on the device, so the cool region and the non-cooled region. Everything else is kind of self-explanatory as constants, which will be given to you in Excel file.
The areas of which are going to be cooled are the thenar region, and the reference temperature is going to be the hyperthenar region. These areas are chosen because they're classed as peripheries, and they're also areas of good circulation. So when this is cooled through the heatsink and the Peltier device, the reference temperature will be coming from this part of the hand here. Okay, this is the device itself. As you can see, there is a fan and a heatsink combination, so the fan spins, and then hopefully to remove heat from the base of the heatsink, which is connected to a Peltier device. A Peltier device is known as a thermoelectric cooler, and it contains a hot side and a cool side, so there's a temperature difference. In order for the cold side to be as cold as possible, the hot side needs to be as cold as possible. Hence, that's why we're using the heatsink to remove all the heat. As you can see, it's been lovingly blue tacked together by the electrical engineers. So it will sit on your hand as shown. An RTD, which is a small white dot there, will record the temperature of the cooled area on the thenar region of the hand, and the white dot there, another RTD, will record the temperature of the reference temperature, which is the hyperthenar region. And it'll sit in your hand just as shown. But hopefully, with the next project, we're looking to add a foam grip, so rather than it being a piece of plastic in your hand, which can be quite uncomfortable, there'll be a bit of foam. It'll curve to your hand, making it more ergonomically friendly. This is the data acquisition device that's used within the project. It's the MyReal by National Instruments. Everything's going to be connected through connector B. This includes the RTD, the heat flux sensor, and the fan, and the Peltier device, so everything can be controlled from the front panel, which will be shown later on. It's pretty easy to use. Plug in the top. There's a plug that's provided in the briefcase itself, which connects to all the ports of information coming in. However, it could be easier to use the USB. It can be used with Wi-Fi, but obviously that can be programmed later on. It's very easy to use with regards to programming. I mean, it's just simple. Kind of pick a picture, pick a port, and off you go. This is the case in which the device comes in. As you can see, it's a really nifty looking briefcase, so you're going to get to carry that around university with you, and everyone going, oh, what's in the briefcase? Very good. This is the power cable, so the power comes in, and this is the HD plug, which is going to be connected to the device itself. There's a space at the back of the device in which the HD plug will be able to be connected. So information comes in from the device and is then passed into the system, into the MyReal. The MyReal is a data acquisition system provided by National Instruments. Don't get me started on how much of a nuisance it's been, but it will then allow us to see the data live on a screen using a LabVIEW front panel, and will allow us to see what's actually happening during the experiment and what heat fluxes will be generated. There's an amplifier within the system, which is here. This allows us to get actual usable values from the RTDs, since the RTDs are so small. There's an LCD screen which can be programmed later on to show results to the physicians rather than them reading off a screen. It allows us patients to see as well if applied in a technical environment. This is the box outside of the case, and as you can see, everything wires up and the device is connected to the HD plug. It all comes in. The case will normally have a roof on it, and everything can then be stored back into the briefcase for easy travel. This is the programming side of the MyReal. Everything you can see here is all the inputs and outputs of the device. So we have the RTDs incoming up here in the top corner. So this is where your temperature is going to come in. Constants are derived from the manufacturer, and an RTD converter displays the value on a display which can be seen on the front panel, which is here. So there's the hyperthenar and the thenar region. They're your temperatures, and they'll change when the device is turned on. There is a hot and cold sensor as well, hot and cold display as well. This shows the temperature difference which can be applied to your equation, or will be applied to your equation. What we're looking to see is the heat flux as well, and there's an indicator for that, and as you can see, it is wired up through the same kind of means as the RTDs. This is all then contained within a loop, so it can run continuously until obviously told to stop, which is down in the bottom corner, and once that's done, everything's written into a measurement file, which in this case will be an Excel file, and therefore graphs can be then plotted and information can be analysed, and it can be then saved into a file, so you can then have a record of who's been tested, etc. So which is obviously useful in the clinical environment.